By now, you must have got a good hold on the concepts related to mirrors. Want to explore the phenomena related to light more? Let us see. Till now, we were dealing with light traveling in air only, that is, light traveling in one medium. Now let us see what happens when light travels from air to another medium. Is there any change in the path of light? Let us take some everyday examples. Have you ever seen a pencil half dipped in water? Does it look displaced at the air-water interface? You must have seen that even a lemon appears bigger when kept in a glass tumbler filled with water. So, you want to solve these mysteries? Let us consider the first case of a pencil dipped in water. The part of the pencil dipped in water appears to be a bit displaced. That is, light is coming from a different direction. Now consider if I replace the water with kerosene oil. Again I see that the pencil is a bit displaced at the oil-air interface, but the magnitude of this displacement is different from that of water. Thus, the magnitude of displacement will be different as we use different media. From these observations, we can say that light does not travel in the same direction in all the media. When a ray of light is traveling at an angle and passes from one medium to other, light faces a change in direction in the second medium. This phenomena is called refraction. Refraction can be defined as the bending of light when light travels from one medium to the other where there is a difference in the speed of light in both the mediums. So, let us perform a few activities and understand refraction better. Take a white sheet of paper and place it on a wooden board. Now, fix this sheet on the board and place a glass slab on that sheet. Draw the outline of the glass slab and mark the corner points as A, B, C and D. Now draw a line at an angle to the glass slab which meets the line AB at the point O. Now mark 2 points on that line and place pins at those points. Let us call those points E and F. Now view the pins kept at points E and F from other side of the slab. Take 2 fresh pins and place those 2 pins in such a way that all the 4 pins are in the same straight line. Now mark the 2 new points as X and Y. Join the line XY such that the extension of the line meets the line CD at O'. Now remove the glass slab and join the points O and O'. You will find that light is changing its path at O and O'. Now draw a normal at the point O and name it N dash, and at point O dash draw a normal and name it M dash. From our diagram we can see that when a light ray travels from air to glass, it is bending towards the normal, and when a light ray is exiting the glass, it is bending away from normal. Thus, we can generalize that when light travels from a rarer medium to a denser medium, the light ray bends towards the normal, and when a light ray travels from a denser medium to a rarer medium, the light ray bends away from normal. Also, from the diagram we see that the emergent ray is parallel to the incident ray. Why is that so? This is because the extent of bending of light at the interface AB and CD is equal and opposite. This is the reason our emergent ray is parallel to the incident ray. Now consider the case when a light ray falls normal to the interface. In this case, the light ray does not bend at all and it passes through the medium without bending. You can check this yourself by repeating the activity we just performed. Just place the 2 pins at the normal N dash and you will get the result. Now consider one more example of refraction. You have generally seen a coin appears to be raised when kept in a glass tumbler. Why is this so? We know that refraction is the cause of this, but let us understand it better with the help of a ray diagram. Consider 2 light rays emerging from the coin. The first light ray strikes the interface normal, which passes without bending. The second light ray refracts away from normal as it passes from a denser to a rarer medium. If I trace back the second light ray, I see it meets the first light ray just above the coin. Therefore, we get the virtual image of the coin which is just above the coin which explains the reason why a coin surface appears to be elevated. Just like laws of reflection, refraction also follows certain laws. The first law is the incident ray, the refracted ray and the normal to the two transparent media at the point of incidence all lie in the same plane. The second law is the ratio of the sine of angle of incidence to the sine of angle of refraction is a constant for a given pair of media and a given color of light. This law is known as the Snell's law of refraction. If I is the angle of incidence and r is the angle of refraction, then sin I divided by sin r is a constant. Let us find out what the constant is in the Snell's law of refraction. But before that, let us understand a few terms. We are already familiar with mass density, and just similar to that is optical density. Optical density is how rarer or denser a certain medium is. That is, the ease with which light can pass through a certain medium. An optically dense medium highly resists light passing through it, whereas an optically rarer medium allows light to easily pass through it. Optical density is expressed in the terms of refractive index, which is represented by n and is a constant for a certain material. To calculate the value of refractive index, it is simply the ratio of speed of light in vacuum divided by the speed of light in the material. Thus, we can say refractive index is basically a measure the difficulty light has to face when it passes through a material. If the value of refractive index for a certain material is low, this means that light can easily pass through it, compared to a material with higher refractive index. Note that the speed of light in vacuum is 3 into 10 raised to power 8 meter per second, which is the fastest, and in any other material, the speed of light will be slower than this. Thus, we can say for any material, the value of refractive index will always be greater than 1. In the Snell's law we just introduced, the ratio of sin I and sin r was equal to a constant, and this constant is nothing but the refractive index of the material. Also, note that when a light ray travels from a rarer to a denser medium, it slows down and bends towards the normal, and when the light ray travels from a denser to a rarer medium, it speeds up and bends away from normal. Just like we define relative density, let us define relative refractive index. It is equal to the refractive index of one medium with respect to other. Consider medium 1 whose refractive index is n1 and a medium 2 whose refractive index is n2. Then the refractive index of medium 1 with respect to medium 2 would be equal to c by v1 whole divided by c by v2, where c is the speed of light in vacuum, v1 is the speed of light in medium 1 and v2 is the speed of light in medium 2. Thus, on solving this equation, we get the refractive index of medium 1 with respect to medium 2 is equal to v2 by v1, and we represent refractive index of medium 1 with respect to medium 2 as n12. The refractive index of medium 2 with respect to medium 1 is equal to n2 by n1, which is further equal to v1 by v2. The refractive index of a medium with respect to vacuum is called the absolute refractive index or simply the refractive index and is denoted by n. So let us quickly recap what we learnt in this lesson. We understood the behavior of light when it travels from a rarer to denser medium and from a denser to rarer medium. We studied the laws of refraction and we introduced refractive index and discussed its importance.